This is Where We Live from Connecticut Public Radio. I'm Patrick Scahill in for Lucy Nalpathanchel. They're the coded engines driving big companies like Google, Facebook, and Amazon. Sets of instructions set out in computer code to solve problems. They're called algorithms. But is an algorithm solution always the right one? Do you trust computer programs to make decisions in your life? Join the conversation 860-275-7266 or find us on Facebook and Twitter at Where We Live. Later this hour, we will explore the biases and problems that can come up with algorithms, but right now we turn our attention to the basics of how these chunks of computer code work. Joining us to help explain that is Christine Chung. She's a computer science professor at Connecticut College and an algorithms researcher. Christine, welcome.
Hi.
So for starters, let's just talk a bit about what an algorithm is. So what is an algorithm, Christine?
An algorithm is, just as you kind of just put it, it's a set of instructions, step-by-step instructions to follow. There sort of is, I guess, a lot of mystery around the word sometimes, but almost by definition, they're not mysterious because they're clear-cut. You can think of them as an enumerated list of, 1, 2, 3 instructions. An everyday example would be, like the steps we follow for washing our hands. We start by turning on the water and then getting some soap and then rinsing our hands off and then toweling dry. So even daily routines like that can be thought of as algorithms informally. Another kind of maybe more interesting one that the computer scientists like to joke about is when you go in the shower to shampoo your hair, and the back of the shampoo bottle actually has the algorithm for shampooing your hair written down. It says lather, rinse, repeat. And the sort of silly joke there is that if you were to literally follow those instructions, maybe as a robot would, you would be in the shower indefinitely because every time you hit the instruction to repeat, you would be starting from the top of the instructions again, and you'd never get out of the shower.
So I need some kind of break condition written into these, and on the shampoo bottle that says stop shampooing after the second run.
Exactly. So
but humans can figure that out, but for computers, you need to really spell it out.
Yeah, exactly. You have to be very literal and very clear cut in what you're telling them to do. So those are sort of informal descriptions of some daily routines that are algorithms.
So you teach students a lot about algorithms, and you started by saying there are things that people often conceive of as mysterious. Why do you think people do hear the word algorithm and they do think of man behind the curtain somewhere doing something?
Yeah, right. So I think the what an algorithm is not the mysterious part. I think what's mysterious about them is that people don't know. For more interesting problems like more interesting than washing your hands or washing your hair. People don't know what the steps are, right? They wonder, they have no idea what these clear-cut instructions often are for, what your GPS does, which is map you in the fastest route from point A to point B. But, the thing I would sort of argue is that, that's only because they lack the exposure and some practice that we have, like as computer scientists. And after, maybe taking a class or two or doing some reading online and reading these algorithms step by step, you start to see that there's actually, you can actually follow them usually, especially if they're written kind of in plain English as opposed to in code. If you can read an algorithm in what's called pseudocode, which is just more like an English description of the algorithm, then you understand, I can see how that would achieve that goal, And so it ends up not often being very mysterious, although I have to say a lot of these machine learning algorithms are sort of a different beast entirely.
Yeah, and we'll get to that a little bit later on in the show. I mean, and these are algorithms that are almost kind of black box algorithms where the machine is figuring out solutions and the humans maybe aren't even entirely sure how it got from point A to point B. So we'll talk a little bit more about that. But I guess for now, maybe we can talk about, so there's one algorithm that you mentioned to me before the show a few days ago. This is an algorithm, I think it's called the optimal stopping problem or the 37% problem. Maybe I'm misdescribing it or not describing it correctly.
Yeah. Sure.
But talk a bit about how this algorithm works, and I guess we can maybe use the example of I'm a young gentleman trying to date,
Okay,
So
sure.
so in that context, yeah, I'm not. By the way, I'm not. I'm a happily married person. but just describe how this works.
Yeah, sure. So probably the name that the most basic version of the problem goes by most often is called the secretary problem, sort of like this antiquated name. But in the version of the story where it's a young single person looking for their mate, the question asks, the problem is, how many people should you kind of like play the field with, date around, see what's out there before you start to sort of get serious about settling down and looking for your like future spouse.
So sort of how long am I going to look before I leap, essentially?
Yeah, right. That's the terminology from and so.
And by the way, I bring up the dating example because I think Kepler actually kind of did this way back when his first wife either passed away
right.
and he ended up dating, I think, 11 people and eventually settled on the fifth one or something like that.
Right. Although I think in his case, he sort of went back to someone he had already passed on. He had moved on from that person and then went back. In the most simple version of the algorithm, we make this assumption that, you can imagine the scenario of hiring someone for an open job position you have. It's sort of a similar situation, right? You're like evaluating candidates one by one in sequence, and the assumption is that after you pass on a candidate and go to the next one to evaluate them, you don't get to go back to the previous ones, and it's in under that assumption that it turns out there's just this sort of very simple, clear-cut rule that's the optimal way of ensuring you get the best, of not ensuring, but the optimal way of picking the best candidate, in the sense that it's the best chance of getting the best candidate.
Right.
And so the algorithm is that you take 37% of your candidate pool. So if you're in the dating scenario, it's 37% of perhaps the number of people you expect to date in your lifetime, to be able to date potentially. And then after the 37% mark, you during that time, during the first phase of the 37%, you just do evaluations, not for the sake of possibly making any offers or settling down with anyone, but just to play the field, to see what's out there, to see what the range of.
I'm keeping detailed notes on every person. This is a good quality, this is a bad quality, and then I get to this point, as you're saying,
right.
where it's like, okay, I have all this data now. It's time for me to make a decision.
Right. Actually, it's not even. You don't even need detailed notes in the algorithm. All you need to know is who was the best one you saw so far. That's all. So you don't even need to think very hard or justify why. You just have this like instinctual, I like this person best so far of all the people. And then after the 37% of them go by, you can move to this phase where like, okay, now the next person who is better than all the rest of the people I've seen, that's the person I'm going to, try to marry or make the job offer to.
And so naturally that works out perfectly every time.
Right. It only works right. So it only works out that you get the very best candidate using that algorithm 37% of the time. Somehow the percentage of the time it works out is the same as the percentage of the time you spent doing the data collection, the quote data collection phase.
So 67 or 63% of the time, I can't do math quickly in my head, as you're gathering, but it's wrong more often than it's right, essentially.
Yeah.
Yet it's consistently right at this rate.
Yes, right. You can so the reason this is, more formally an algorithm than, say, the daily routines that are algorithms is that we can prove things about it. Like that's what if you're a purist, that's the only thing you can call an algorithm is something you can prove will do optimally every time, for example. So we can prove that this algorithm will, like you said, although it fails 63% of the time, 37% of the time will give you the best candidate, and that's the best possible algorithm. You can't find an algorithm that will give you a better shot than 37% of the time getting the best candidate. So,
are there other algorithms that are out there where we do have that provenance or that provability repeatedly when we do them? And if so, can you maybe just briefly talk about some of those?
Yeah. So, for sure. Yeah. There's lots of these. I mean, they're all, they're all around us every day. And, like one maybe daily example of such an algorithm is the algorithm we use for changing, like if you're a cashier, for making change, right? So when you are a cashier and you need to make a certain amount of change, what's your algorithm? Say you want to make 87 cents of change. You will start from the largest denomination coin. You look at your quarters, right? And you say, okay, how many quarters can I take before I go over the total change that I'm making, that I'm trying to make? So for 87 cents, it'd be 3 quarters. Then the algorithm says go to the next smallest coin, which is a dime, and take as many of those as you can without going over, and so on, all the way down to pennies. And, this algorithm, I can formally call an algorithm because we can say provably that the number of coins you use at the end will be the minimum possible number for making the change equal the amount you were trying to make, And the other reason this is a more like formal algorithm is because it has this feature of working no matter what the input is, right? The input values, there's an infinite possible number of input values. It could be any amount of change you want to make, and you can execute this algorithm where you go from biggest quarters down to pennies, and you always end up with the smallest number of coins needed. And that you can prove that. And the interesting kind of thing about this example is that it only works because of the denominations of coins we've picked, right? Like if someone decided one day we should have a 30-cent coin, and then we suddenly started circulating 30-cent coins, it wouldn't, and then you had to make 50 cents a change. The optimal solution would be to skip over the 30-cent coin and do the 2 quarters. But so it's the denominations that we've chosen that allow the algorithm to be provably optimal.
There was, I remember reading some articles, I think like 10 years ago, where there was a paper that said, what would be really efficient? An 18-cent coin. and if we had an 18-cent coin, that would reduce the number of, nickels, dimes, whatever, to the optimal limit for people making change. But then I got to this idea of, 18 times 3, that's hard. That's hard math for someone like me.
Right, true, right.
Which is difficult. So, there's a computer doing one thing, and then there's humans doing algorithms. And humans have been doing algorithms for generations. I mean, this goes back well beyond change, right? I mean, this is something that goes well back in the history of mathematics.
Mm-hmm. Yeah, definitely. So we can definitely talk about history. But back to the changes example for a second, the denominations, luckily, there's so many different possibilities. So luckily, you can find ones that are easy for humans and work for the computer.
Yeah.
But in terms of the history, the algorithms have been around, I would say they're almost part of the human condition, like from the beginning of time, but maybe more formal algorithms started way back, like in 2000 BC when the ancient Egyptians figured out, or at least maybe they weren't the first ones to figure it out, but they were writing down and teaching the protocol for multiplying 2 numbers that, we learn in grade school, where it's like a multi-digit number that you have to multiply against another number, and you do kind of you line them up, column on top of each other, column by column, and you go through. So all the, young children that are in school today are learning this algorithm. And that was before the word algorithm existed. There was also algorithms that are very famous from Euclid's writing in like the 3rd or 4th century BC, like for finding the greatest common divisor, for example. And then it wasn't until the 9th century that there was the kind of source of the word algorithm was this Persian mathematician whose last name, his name was Abu Abdullah Muhammad al-Khwarizmi, and I'm sure I butchered the pronunciation, but his name, al-Khwarizmi, sort of over time morphed into this word algorithm because he wrote the book, like the textbook on algebra. And it wasn't called algebra. It was the Persian word. And then that word sounds like algebra, so it morphed into the word algebra. And in that book, he gave algorithms for doing things that we all learned to do in like high school algebra, like solving equations, like solving a linear equation, solving a quadratic equation. So somehow over time, being Latinized and then being used in various ways over time, his name came to take on this meaning of algorithm.
Yeah. So I think we're going to take a little bit of a break here. We're going to come back. We're going to talk maybe a little bit about sort of the limits of algorithms. There's something called NP, hard problems, and you're going to explain to me what that means. It sounds difficult. It is difficult, actually. It's one of the most difficult things in math, is my understanding. This is Where We Live. I'm Patrick Scahill, and we'll be back after this. You can join the conversation by calling 860-275-7266 or find us on Facebook and Twitter at Where We Live. This is Where We Live from Connecticut Public Radio. I'm Patrick Scahill in for Lucy Nalpathanchel. Today we're talking about algorithms, instructions for computers that pop up in everything from GPS directions to Google searches. Last segment we spent a little time talking about how algorithms work, but what about when they don't? There are some problems that seem simple, which in reality are actually really tough for computers to crack. With us is Christine Chung. She's a computer science professor at Connecticut College and an algorithms researcher. You can join our conversation right now, 860-275-7266. You can find us on Facebook and Twitter at Where We Live. So Christine, last segment we were talking a bit about sort of the basics of algorithms and I guess algorithmic thinking. But algorithms don't work all the time. And there actually are some problems that I probably could explain to my young nephew that are really tough for computers to crack. So talk a little bit about this.
Yeah, sure. I'd love to. So one, I guess, very well-known such problem is called the traveling salesperson problem, where you're, trying to travel around to different cities. So you have a set of cities that you want to visit each one exactly once. And so you need to take a tour of these cities, but you want to do so in a way that minimizes the total, say, cost of your traveling to these cities, or maybe the time, whatever it is that you want to minimize. But this is an example of an algorithm that, is of a problem, I should say, not an algorithm, a problem that is easy to state to, anyone that's, in middle school. And yet there's no known efficient algorithm for solving the problem. Of course, you can try every possible path through the cities, every permutation of the cities. You can always sort of brute force, exhaustively search through all the possibilities, but that would just take too long. Like it would be a totally impractical, useless algorithm. And so normally what we have to do in cases like this is find some clever way to essentially like prune that search space. And in this case, in the case of this problem, no one has been able to find a way, and it's sort of more that no one has been able to find a way, but that there's this. It's part of this whole larger class of problems that no one has been able to find an efficient solution for. Another great example for little kids is the map coloring problem, which is
the map coloring problem.
Yeah,
okay,
map coloring. Mm-hmm. So you're given 3 colors, like 3 crayons or 3 markers. And like say red, blue, and green. And you have a map in front of you that is not colored in. So say like a map of the United States. And the goal is to color the map in a way that so you put a color on each state, each region, in a way that no 2 neighboring regions share the same color. The way you normally see a map being colored, so that it illustrates the distinction between regions. And whether or not that's possible with 3 colors on any given map is not something that can be decided by an efficient algorithm.
So these are a class of problems where conceivably a computer could get the answer.
Yes.
But essentially a computer can only do X number of computations per second.
Yeah.
There are a astronomical amount of possible solutions out there. So literally for the computer to march through every permutation would take more time than like our star is going to burn in the sky, basically.
Yeah, exactly.
Which is, I mean, but we think maybe there is a way to write an algorithm that could crack this. This is a debate among computer scientists right now, right?
Right, it sort of is. So I guess so the problem actually it comes down to this thing called the P versus NP question. And it's an open question. So yes, what you're saying is true. It's possible someone could find an algorithm for these problems, but the sort of overwhelming consensus is probably that the class of problems P, which is like the problems we can find easy solutions for, fast solutions for, is not equal to NP, which is this larger class that includes these two, the map coloring, the TSP, and that probably there just is no way to find, there is no efficient algorithm for these problems that exists at all. The reason it's still an open question is because no one's proven that P doesn't equal NP. In other words, no one's proven that it's impossible. It's impossible to find an algorithm, and that's like the effort of a lot of complexity theory researchers right now is to try to prove that P does not equal to NP because for the most part, people don't expect that we'll just suddenly find an algorithm for one of these problems. The exciting thing about finding an algorithm for one of them is that if you find an algorithm for one of these problems, then all of them are sort of instantly solved also because they all reduce to one another. There's just this huge set of problems called the NP-complete problems, which include the map coloring, the TSP, and all these problems from all fields of science that are all reducible to one another, and you just need to find one algorithm for one of them. So if you're a kid out there and you're doing a lot of map coloring and you have a good idea, you should let someone know.
It seems like the world would be a less exciting place if someone did find it out. But maybe that's just my own projection. I don't know. So we do have a call coming in from Michael in Ashford. Our number is 860-275-7266. I'm Patrick Scahill in for Lucy Nalpathanchel, and you are listening to Where We Live. Michael in Ashford, you're on the air. Hi.
Hey, thanks, guys. This is a fascinating topic. You said when you were talking about the beginning of algorithmic thinking, you went back to like ancient Egypt and, human civ. But I believe that dogs, and probably primates also have algorithmic patterns and kind of routines. And I think most dog owners would say, yeah, that's right. They'll mark like, okay, that's a yellow jacket nest. I'm going to detour, and then they employ it systematically.
Yeah, well, Michael, thank you so much for the call. I think it's a great point. I know my cat is very put off if there's any break in her routine. So what about this idea that, algorithmic or pattern behavior isn't just limited to people, Christine?
Yeah, I've never thought about that before, but and I actually don't really have a pet myself, so I can't speak from personal experience. But I wouldn't doubt it. I mean, I think, having a routine is definitely part of just the human condition, having routines. And I don't see why it couldn't also be part of the sort of, inborn programming of an animal, too. I guess the distinction is when you're talking about something that's maybe more formally considered an algorithm, and you're talking about something basically that you can show provably is going to always work, a procedure that will always work for achieving a certain goal.
Right.
And it'll always, in the sense that for every possible input you give it, it'll always give you the correct output.
Yeah. So I guess getting back to these NP-hard class of problems, you were talking about for algorithms to really be great, they have to be provable. There are ways that we can maybe get at some of these NP-hard problems by kind of approximating the solution. So we're not getting to a provable, repeatable solution every single time, but we can kind of get there. And this is maybe where machine learning comes in?
Yeah. So there's sort of two separate things. So there's approximation algorithms, which is still within the field of algorithms where you're making provable guarantees about your algorithms, but they are not getting the optimal anymore. You're proving that they'll get within some factor of the optimal, and that's no matter what in the worst case. So you're still there's but for the purist, it's still called an algorithm because you're able to make this sort of worst case guarantee that you can say something very clear cut about it. Whereas, machine learning takes a different approach that's much more, in general, you're not going to have a machine learning algorithm that anyone's been able to prove something about. There's definitely a machine learning theory community, but the general way we use machine learning that you hear about, you're not going to have algorithms that each line of code, each instruction in the algorithm was like a clear-cut human reasoned intention. Because like you said before, the machine learning algorithm sort of has evolved by training on data. It's a lot like the way we, raise our humans in a way. You give it some frameworks, you give it some inborn, like the system in their brains is set there, and then you give them experiences, data to train on, and then they evolve in this way that's not totally under you're not aware of every single line of code in their head anymore.
So I'm Patrick Scahill. This is Where We Live. I'm in for Lucy Nalpathanchel. That was Christine Chung. She's a computer science professor at Connecticut College. She's an algorithms researcher. Joining us now via Skype is Karen Hao. She is a artificial intelligence reporter for MIT Technological Review, and she also writes a weekly AI newsletter called Algorithm. Karen, hello.
Hi, Patrick.
Hi.
Thank you so much for having me.
Of course. We're happy to have you. So we've been talking a bit about algorithms and kind of how they work and some of the limits that they bump up against. I guess to this machine learning question, maybe we should just step back for a second, Karen, and explain what machine learning is. So what is it? And is there an example that you give to kind of explain it to dummies like me for how it works?
Yeah, absolutely. So building off of what Dr. Chung said, you have the algorithms that you use in your everyday, and those are simple enough that you can write an explicit series of rules about them, like the change example that she gave. But machine learning algorithms, essentially, they tackle problems where it is complex enough where you, as a human, don't necessarily know explicitly what the most efficient rule set is to achieve whatever problem you're trying to tackle. So instead, you give all this data and everything that you want to a computer, and then the computer is the one that's figuring out the most efficient rule set. And so this is like a category of techniques that fall under the much larger computer science field of artificial intelligence. And the way that I most simply explain it in a phrase is machine learning is just really, really good at finding patterns in data and then ultimately applying those patterns to whatever task at hand. So the example that I love giving is Netflix recommendation algorithms. So if you'll notice, your Netflix is probably quite good at predicting what shows that you like watching, what movies you like watching. And they do not actually use a rule-based algorithm. The algorithm doesn't say, oh, look at the person's genre, and if they like one genre, then feed them more TV shows of the same genre. What it does is it'll say, look at the genre, look at the actors and actresses' names, look at the length of the show, look at all of these different characteristics of the movie, and you figure out, computer, what you think is actually the most predictive of what they like. And perhaps it'll be something as niche as this person really likes strong female leads, so we are going to feed them more shows with strong female leads. But from a human perspective, because of the complexity of the algorithm, we might not actually be able to interpret exactly what rule the machine discovered.
And so, Christine, this is a case where the computer is essentially almost building the algorithm on its own?
Yeah. I mean, at the end of the day, I think Karen's example is so good, and she's explaining it really clearly. But at the end of the day, the machine learning algorithm is still a piece of code that's a line by line. You can read it, you can see it. What's sort of the underlying mystery, I guess, is how it's evolved the parameter settings, right? And those parameter settings, as Karen put it, are developed over time from training the algorithm, and then the way that the Netflix recommender works is you notice is kind of similar to if you had a human that was able to see what you were watching and could notice the pattern that, oh, you like movies with these strong female leads, or TV shows. I know another TV show that is like that. So it's bio-inspired computing, and it is actually a lot. Emulates a lot the way we learn. The way we make decisions ourselves based on patterns we've seen and experiences we've had.
So I know machine learning is a term I've heard thrown around in computer science often, Karen. Another term is deep learning, which is my understanding of that is this is another type of machine learning. Can you just sort of explain what deep learning is and what the nuance there is?
Yeah, sure. So deep learning is another subcategory of machine learning. So if AI is the giant umbrella, then machine learning is under that, and then deep learning is under that. And it is a form of machine learning, but the software that you are using is specifically a neural network. And a neural network is, as Dr. Chung was saying, machine learning is bio-inspired. So the neural network is a piece of software that was designed to mimic the brain. So there are these really simple computational nodes that are supposed to mimic your neurons, and then they're connected in a way that's supposed to mimic the way that your neurons connect to make decisions in your brain. And deep learning, whereas machine learning is really good at finding patterns in supposedly any kind of data. You could have small data or very, very large data. Deep learning is specifically for massive data. And so Google would definitely use deep learning. Facebook would use deep learning because of the scale of the data that they have at their disposal. And the thing that gets kind of more complicated with deep learning is because of the way that neural networks are designed, it is much harder to interpret why it decides to make certain decisions, whereas some machine learning techniques are a bit more transparent and a bit more interpretable to humans. Deep learning, it can be really, really hard.
We have a question from Peter in Farmington, who actually has a question, I think, about Google. Peter, go ahead. You're on the air.
Hi. Yeah, I actually have a question about the Google DeepMind. So they developed a software that they played it on a computer game called StarCraft, which they played it against real players anonymously. So they had a control group essentially, and so they did a bunch of research and played the computer against people. But I'm just wondering where something like that could be applied, because I understand that you have deep learning and algorithms to see to detect patterns, but something like this is strategy.
Yeah,
that's a great question.
Peter, great question. Karen, go ahead.
Yeah, so DeepMind is the division that specifically is working on artificial general intelligence at Alphabet, Google's parent company. And they specifically popularized this technique known as reinforcement learning, which is it's a type of machine learning where essentially it's mimicking the way that you would train an animal. So if you think about Pavlov's dog, where you ring the bell and then deliver it food, so it learns to salivate every time you ring the bell. With reinforcement learning, you essentially give the machine learning algorithm an objective and then let it explore and do random things. And every time it ends up accidentally going towards the goal, you give it rewards, and every time it goes away from the goal, you take away rewards, and that's usually in the form of giving it points versus subtracting points from it. This technique can get very sophisticated in that you can allow it to learn something like StarCraft, where it is just haphazardly kind of trying everything out in the game. And then every time it wins a game, you say, yes, that was the correct thing to do. Now log that as experience that you do want to use. And every time it loses the game, you say, no, that's the incorrect thing to do. Don't try doing that again. And so this technique, DeepMind, has been trying on various different things to really push the bounds and see how complex a problem an algorithm can solve using this technique. And the goal is to eventually be able to apply it to many things in the real world. Reinforcement learning is, in theory, really important for self-driving cars, for example. If you have a self-driving car on the road, you won't always be able to know what all of the other cars on the road or other pedestrians on the road are going to do. And so you want to imbue the self-driving car with some ability to figure out in that moment, given all of the things around it, what is the safest path to drive forward? And so that's kind of a more real world application of reinforcement learning.
Christine and Karen, as we're talking here, I can't help but think that, these algorithms are functioning essentially as, in some cases, really, really big, large-scale statistical correlation engines. Something goes in, something comes out. There isn't maybe room for serendipity there. There isn't room for, when I was a kid, I would walk into a bookstore and I would see a cover that would call out to me on a book, and I'd say, I want to get that one. Now Amazon tells me, well, I read this sci-fi novel. I want X number of more sci-fi novels. We have a listener on Twitter who was kind of getting to this point saying, well, can't you just tweak an algorithm by, going outside of what they recommend and then you get more things? I know in my case, sometimes I'm on Netflix, Christine, I'm actively avoiding shows because I don't want it to screw up the algorithm. So just talk about this idea. I mean, what has happened to serendipity in this world of all this stuff that's tailored and sent to us?
Yeah, I definitely, my husband sort of feels the same way. He doesn't like the fact that, the recommendations he's getting, and basically every experience online now is tailored toward you by these machine learning algorithms, by the AI. And so it's taking away that sort of even more natural experience of accidentally finding things or finding something that branching out and doing something you wouldn't normally have done. And I think your approach makes a lot of sense to try to almost, or the Twitter posters approach to try to almost play with the algorithm, try to trick the algorithm a little bit, or and just know that there's this AI that's serving you all the ads you see, all the content you see online, and just be aware of that fact as you're going online. And you can use tricks to incognito tabs on the web browser to try to be someone other than yourself for a while.
From Connecticut Public Radio, this is Where We Live. I'm Patrick Scahill, in for Lucy Nalpathanchel. I want to say thank you to Christine Chung. She's a computer science professor at Connecticut College, and she's an algorithms researcher. Christine, this has been great. Thank you so much for taking the time to come up here today.
Thank you so much.
Coming up, we're going to talk about some of the problems with algorithms beyond just trying to tweak your Netflix recommendations. Biases, incomplete data, and a lack of accountability. These are serious problems. Do you trust the computer code that's making decisions for you in your life? You can join the conversation by calling 860-275-7266 or find us on Facebook and Twitter at Where We Live. This is Where We Live from Connecticut Public Radio. I'm Patrick Scahill, in for Lucy Nalpathanchel. Thanks for listening today. If you are unable to listen live mornings at 9 or evenings at 7, you can also subscribe to Where We Live on Apple Podcasts, Stitcher, Spotify, or any podcast app. Also, make sure to follow us on Instagram at WNPR. Today, we're talking about algorithms, the decisions computers make in our everyday life. Joining us via Skype is Karen Hao. She's an artificial intelligence reporter for MIT Technological Review. She also writes a weekly AI newsletter called Algorithm. Joining us now by phone is Mitali Nkonde. She's a fellow at the Berkman Klein Center for Internet and Society at Harvard University. Mitali, welcome to the show.
Hey, thank you for having me on. It's great to be here.
So, Mitali, a lot of the conversation today has focused on algorithms, but you've written that we need to look at sort of who is behind those algorithms, the people writing the code. So talk a bit about why that's important.
Yeah, so I've been working on AI governance, which is a burgeoning field. And the reason that it's arisen is, as your viewers have heard earlier in the conversation, algorithmic decision making is being used increasingly to make massive decisions in our lives. And that's certainly true of the public sector. So in my field and in my view, one of the concerns that I have are that algorithms are optimized to serve the needs of the people that design them. So, for example, if you are somebody that is interested in playing a strategy game or has a self-driving car, you may have a completely different positionality than the people whose lives, who are being told whether they can keep or have their children taken away by algorithmic decision-making, or whether or not they're going to get bail. And in these cases, one of the things that we're finding is that algorithmic decision-making systems show the same biases that we have in society. So one really famous example that many of us know in the AI governance space is the COMPAS algorithm, which is used by about 40 states across the country to decide whether defendants get bail. And ProPublica did this huge investigation where they found that particular algorithm always favored white defendants and gave them lighter bail determinations than their black defendants with exactly the same profile. And the reason that was shocking from a governance perspective is that we are looking for this idea of base fairness across society, and the assumption is that algorithmic decision-making systems are mathematical, they're looking at data, they're looking at patterns, they're going to be impartial, and the evidence suggests that that's not actually the case. And we see this across a number of different algorithms. We see it in child protective services, we see it in housing, we see it in education. And the theories that we have are because the people that are developing the algorithms are typically middle-class white males on one of the coasts, they don't really understand the material and lived conditions around the way these people are living their lives, so they don't understand the decision-making processes. And because they don't understand the decision-making processes, they actually encode their own biases and oversights into systems. And that is obviously a massive problem because if we're dealing with child protective services, that's the question of whether a family gets to stay together or be apart. And that's really where the bulk of my research and the bulk of my work really lies, around how do we make these technical systems that are being developed by private companies make decisions in a public sector setting.
And I want to get to that idea of transparency in just a couple of minutes here, Mutale. Karen, I wonder if you can just talk a bit to this idea of maybe there are some problems, maybe there are some policing, for example, maybe some fields where algorithms or machine learning, however well-intentioned it may be, maybe we should just have algorithms kind of steer clear of those areas?
Yeah, that's a really great question. And I think that's very heavily debated within the AI ethics and AI research communities. To build off of what Mutale is talking about, I mean, machine learning fundamentally is about finding patterns in data. And unfortunately, that it doesn't always make sense to perpetuate patterns from history into the future, because we don't want to repeat history. We want to advance society and hopefully improve and not keep mimicking or replaying the same patterns over and over again. And so if you decide to apply a machine learning algorithm to something that you might not, that fundamentally has this problem, like Mutale giving the COMPAS example, that's a great example. You are looking at historical patterns of who usually, like which defendants usually have been incarcerated within our criminal justice system in the past, and you're just blindly kind of replicating that into the future without actually thinking about whether the past did good. Is that like what we are actually striving for? Another example is listeners may have heard of the story that broke where Amazon tried to build an internal hiring tool with a machine learning algorithm. And so they fed all of the resumes that they previously received and the candidates that they had selected, and the algorithm basically learned over time that women were not good candidates. And so that's another example where, historical decisions don't necessarily make great future decisions. And so there's certainly what I like to do when I talk with AI researchers or other people within this field is to ask them, should you even be applying machine learning to this problem at all?
And so, Mitali, I guess this gets to my next question, which is, okay, so it sounds like we might need some oversight here. Do we need regulatory oversight of these machine learning systems? Do we need sort of like an FDA for algorithms that's been described in papers? Is that something that you think would be beneficial to help control what these algorithms can do and direct sort of how these companies function?
I would definitely say that. I was part of the team that introduced the Algorithmic Accountability Act in June of this year to the House. And one of the things that we looked at, well, there are two things. Every other industry in this country is regulated. And so why wouldn't this one be, number one? And then the second thing is algorithms are not this isn't magic. These are systems that are driving how we live and shaping humanity. And if we want to be able to decide the direction that we get to, I think Karen really got to it beautifully. But one of the things that I would ask is, if we want a just society, if we want a society that can move towards racial justice, can move towards gender justice, we cannot rely on decision-making processes that are completely dependent on training on our past mistakes as well as our past successes. So one of the ways that we can really interject, particularly when you're looking at vulnerable communities, is having these regulatory oversights. My particular favorite are impact assessments. Why can't we do control tests where we see how this algorithm works in real time? Because the other thing, and I know we are going to get to transparency, but because of IP law, we also don't really know how these algorithms are making decisions. So from a policy perspective, I can analyze the results and see that these results are expressing racial or gender or ableism bias, for example. But I am still limited under current law to finding out how to fix that problem. So that's one example where regulation would give those of us that are interested in, we love technology, we want to use it in the public good, but we need all the information to make that happen. And it really is around values. Who are we as Americans? Where are we going forward as a country? And if we are deciding, and I actually really like the idea that we have algorithmic decision making to help us sort through our data, I just think that we need a way of making sure it's not going to unintentionally or intentionally harm vulnerable populations.
And so, Karen, we have about 1 minute here, and I'm going to ask you a question that's completely too large for 1 minute. But on the whole, algorithms net positive, net negative for society?
Oh, gosh.
I told you it was big. That's an NP hard problem.
I think what's important is that it needs to be a debate, and that needs to be a public debate.
Great. Well, Karen, thank you so much. I want to say thank you to Mitali Nkonde. She's a fellow at the Berkman Klein Center for Internet and Society at Harvard University. Karen Howe, artificial intelligence reporter for MI Technological Review, writes a weekly newsletter called Algorithm. I'm Patrick Scahill. You were listening to Where We Live on Connecticut Public Radio. Today's show was produced by Carmen Baskoff. I want to say thank you to our technical producer, Kyone Wolf, and thanks to you for listening. We'll be back next week. Thanks again.